In this video, we're going to start to discuss molecular orbital theory. So in molecular orbital theory, this is going to give us an idea of how electrons are arranged and therefore how we think about bonding, right, between atoms in a molecule. So unlike atomic orbitals, like let's say we have a hydrogen atom. I'm just going to put the dot here to emphasize the electron, right? We know that this electron is going to reside in a 1s orbital, and the shape of a 1s orbital is going to be spherical with the nucleus in the middle. Okay, and as we discussed before, right, what that orbital indicates is some defined probability of finding the electron within that space. And so that shape of that orbital is spherical for a 1s orbital, and we know that there's some probability of finding the electron in this spherical space here. Okay, and so we've discussed that for atoms, and we can think about how the electron density is distributed in that way for an atom. But if we're thinking about molecules, how do we do that? So let's say we want to think about, for instance, hydrogen gas. Okay, so one way to think about this is that hydrogen gas is made from two hydrogen atoms together to form H2. And so there's a bond between the two hydrogen atoms, right? Like so. All right, so again, if we're starting from atomic hydrogen here, right, we know that one of these electrons, the electron in this hydrogen atom, and we're going to give this hydrogen atom a label, so we're going to call it hydrogen A. So is going to reside in a 1s orbital, and so we're also going to give this a label, so 1s of HA. And then we have a second 1s orbital from the second hydrogen atom, which we call B. Right. And so what we can think about then is that the resulting molecular orbital, as we will call them, right, is going to be a result of some sort of interaction between the two atomic orbitals of the two hydrogen atoms. And so as we discussed before, right, what these actually represent is a wave function, right? And because these are a wave function, if two waves interact, right, they can interact either through constructive interference or destructive interference. All right, and so constructive interference, right, if we think about constructive interference between these two orbitals, what we can think about is we have our, actually we'll just keep it down here. There we go. So for constructive interference, right, we can think of that there being improved overlap, right, in the region that these two interact. So we can just draw the atomic orbitals as if like this, right? And that's going to result in something where there's increased electron density between the two nuclei, okay? And we call this a bonding orbital. Okay? Alternatively, we can have destructive interference. And this will happen, right, if the wave functions are out of phase. So for instance, instead of thinking of the atomic orbitals that have the same phase, what if they have opposite phases? And so we can denote that by, for instance, making this stripe here. And so if we do that, right, these are now out of phase, and they're not going to be able to overlap, or rather, in the places where they do overlap, right, there's going to be destructive interference, and therefore the wave functions are going to cancel out. And so what you end up with then, in this case, is in the places where there would be overlap in this region here between the two nuclei, right? There's destructive interference, and therefore in the resulting molecular orbital, there is no probability of electron density, right? And so what we have here then is, because we do not have this overlap between the nuclei, is we have what's called an antibonding molecular orbital. Okay.